Okay. I hope you had all a happy Thanksgiving and a safe one. I heard a lot of people got sick over the break. So anyway, I think numbers are shrinking, or I don't know, or always in the middle, it's empty. Hello to you as well. Okay, so I know I started this lecture and then you guys had protein characterization after this, so probably you've forgotten all about it. And then of course there's the break. So let's try to refresh what we talked about briefly last time before continuing. Talked about importance of fact characterization. Can you guess or remember anything about why we care about fact characterization? And what do we mean by fact characterization before? So when we say fact characterization, what does this ring a bell?
Type of saturated, unsaturated, super trans fat.
Of course, type of fat. So is it saturated, unsaturated? Do we have cholesterol? Okay, so what else? When we talk about fat characterization, what can we think of, Kevin?
Well, then the other one is like functionality or impact on either your product or whatever. So like melt point, smoking point.
Yes.
Yeah.
Yeah, so characteristic of the oil that might impact functionality or characteristic during processing. So melting point, smoke point, we'll talk about them a little bit, cloud point as well. So physical characteristics, yeah.
Shelf life stability, like oxidative.
Very good. Shelf life stability. So it's very important when we formulate, we think about the types of fat we add, and we also want to think about shelf life when the product is going to become rancid. So we have hydrolytic rancidity and we have oxidative rancidity. So hydrolytic meaning your triglycerides are going to break down and give you free fatty acids. That could happen either through enzymes like lipase, could be endogenous enzymes, or it can happen, let's say you're frying potatoes and potatoes are in moisture and then heat. Moisture and heat are going to break down your triglycerides into free fatty acids. So that's hydrolytic rancidity. And then we have oxidative rancidity. So the more unsaturation you have, the less oxidation you have. The more unsaturation, the less oxidation. It rhymes, but is it correct? The more unsaturation, the more or the less oxidation. Anybody? Wake up. Huh? What?
The more
The more oxidation. Thank you. So unsaturation, you have more double bonds. So you have more places for those double bonds to break down and form peroxides. Okay, so, and then are free fatty acids more prone to oxidation or triglycerides are more prone to oxidation? Free fatty acids. Free fatty acids are more prone to oxidation than fatty acids in esterified to your glycerol. Okay. So some of you did lab today, right? I hope you kind of talked about these concepts. So another one is food safety, right? So if we oxidize, we might get malonylaldehydes, for example, and these are not good for heart diseases. Also, if we get cholesterol oxide, this is a carcinogen as well, for example. Okay, so safety, what else? Processing, we talked a little bit about processing. So refining, what is refining? Do you remember? Those of you that did lab today, did you talk about refining? Okay, yes, go ahead there.
Refining is like removing some of the free fatty acids.
Yes, when you crush the oil, the seeds and get the oil, the crude oil has a high percentage of free fatty acid. Refining takes care of that. So you treat the oil with NaOH, you produce soap, and you centrifuge, you get the soap out, and then you get the oil. So the soap is basically your free fatty acids reacting with your NaOH to give you water and soap. So that gets removed, you kind of enhance the stability of the oil, enhance the flavor, with the exception of olive oil, because the characteristic flavor of virgin olive oil is due to the presence of these crude free fatty acids. Okay, we talked about degree of saturation and then hydrogenation, because you process the oil sometime to produce vegetable butter, margarine. So that's hydrogenation. So basically you use the hydrogenation process to eliminate double bonds and saturate double bonds with hydrogens. So sometimes to test the efficiency of hydrogenation, you do iodine value before and after. So basically you determine the degree of, or the iodine value, you determine that before and after hydrogenation, and then you can see if there is potentially, the process is complete, and then you test the presence of trans fat, because incomplete hydrogenation can cause the formation of trans fat. Okay, I think we covered all of that. Let's move on and talk about physical characteristics. So these are characteristics that you use to identify the oil or to determine certain characteristics that impact processing and texture or functionality. So refractive index is usually used to ID the oil, is a characteristic of different types of oils. Melting point, it's important to know, as if we are, let's say, working with solid fat, we need to know the melting point, because that helps us in determining the effect of different processing conditions on the melting of your fat. Smoke, flash, and fire point, these are important to determine whether or not your oil is good for frying. For example, olive oil have very low smoke, flash, and fire point, or the temperature at which the oil smokes, or you start seeing a spark of, and then, or goes on fire. And that is characteristic, especially if you have virgin olive oil, for example, high in free fatty acid, that will cause a low smoke point, flash point, and fire point. Also, if you use the oil multiple times, that will cause free fatty acids to form. That would reduce the smoke point, flash point, and fire point. So these are also tests that you would do to determine whether or not the oil is done for in terms of use for frying, or whether or not you can use it at different temperatures during different processing. Oh, well, I have a story to tell here about that flash smoke. So I almost burnt my house down one time. So I was, I needed to boil some eggs, and I turned the stove on, but I turned the wrong one on where the oil was instead of the water. And of course, went down to my office to work, came back. I heard the fire alarm going. So the oil was literally on fire. And my daughter was young at the time. And instead of telling her to leave the house, I told her, stay in your room. And what stupid thing I did after that? I took the oil.
You moved it, yeah.
To
The sink.
And did what?
Water. On the water.
Oh.
And then what happened? Of course, I burnt my face, the ceiling. Oh, it was terrible. The good thing was that it was snow outside.
Yeah.
So the next thing I did, I took the pot and I threw it on the snow, and then what happened? Boom. And I shut the door before the neighbor came out. So I was like, it was so embarrassing. Anyways. Yeah, food scientist, right? Why would you do that? I teach this class. Anyway, cold test and cloud point, these both are tests used. Either one of them are used to test the efficiency of winterizing your oil. If you remember last time, I mentioned briefly winterizing the oil. So after you're done with all the refining process, there's also, and then there's deodorizing, but there's also clarifying to remove the waxy material. So what you would do basically is you would lower the temperature, and then the waxes will precipitate, and then you clarify the oil so that if the oil is used in dressing and you put it in the fridge, you don't want it to cloud. So basically, after doing this step, you test to see if you've done it correctly, and then you lower the temperature and you monitor either cloud point or cloud point where you see it start getting cloudy, or cold when you see precipitation. If you don't see cloudiness, if you don't see precipitation, that means winterization was done correctly. Solid fat index, this is important, especially when you are you want to determine, for example, how well your fat can melt, or how well you can spread that butter or margarine. So the higher the solid fat content, the higher will be the melting point, the lower it is your spreadability. And then you can measure consistency and spreadability using a texture analyzer to do that. So these are all physical characteristics. So I will go now into doing the chemical characteristics of the oil. One important test that is very common, and some of you did in the lab this week, on Monday today, and some of you will be doing that on Wednesday. So iodine value. So in a test, when I tell you define iodine value, you're going to tell me this is a test done to measure degree of unsaturation. All right. And you're going to tell me the unit. You're going to say it is grams of iodine absorbed by 100 grams of sample. So these two are important for you to mention. That's why I put them here. Uses of iodine value now. Yes, to determine degree of unsaturation, and that can also be used following a hydrogenation process, determine the efficiency of hydrogenation, and also as an indirect measure of oxidation. So if your oil has oxidized and it's supposed to have a specific iodine value and it turned out to be less than the specific iodine value, that means some of the bonds were saturated. That means they got oxidized. That's why it's an indirect measure of oxidation. All right, so some of you did this today in lab. What you would do is you get your oil, you react it with excess iodine chloride. The more double bonds you have, the more ICL will be used up. Okay, so that's something you want to remember. So the more double bonds, the more you're going to have the action with ICL. The less ICL you have left to react with potassium iodide. This reaction gives you iodine. In that, you will add a starch as an indicator. Iodine and starch will give you a blue color. Then you would titrate with sodium thiosulfate to a clear color. One important thing is the blank, you run a blank. The blank will have, you would need to titrate more to get to colorless for the blank, because all of the ICL will be present in your solution. You don't have any double bonds. So the blank will take the maximum volume of sodium thiosulfate. That's why in your equation here, the blank minus substrate, sample, sorry. So the volume for blank minus the volume of the substrate instead of substrate minus black. That's why I think substrate. Sample, as for sample. Okay, so the volume for black is always larger than the volume for sample. That's why we have blank minus sample volume. You're used to having the blank being 0 or close to 0, and subtract the blank from the sample, but here you have to remember, no double bonds, all of the ICL will be present. You will generate the maximum amount of iodine, then you will have the darkest color needing more volume of sodium thiosulfate to get colors. All right, so the equation here, I'm just going to say that a note to save time. The same derivation we covered for nitrogen analysis for the protein delta. So remember that, review that derivation, then you understand this equation. Okay, I'm not going to repeat that here. But what you have in this equation, it's a percentage, grams per 100 grams. So you have your typical dividing by sample weight, multiplying by 100, okay? So grams per 100 grams. So dividing sample weight, multiplying by 100. What you have here is at equivalence, that means when you reach colorless, equivalence of iodine equals the equivalence of the sodium thiosulfate. So here, the volume times the normality is for your sodium thiosulfide. So blank minus sample volume times the normality of the sodium thiosulfate, whatever normality you're going to use. And what is this value? Can anybody guess what that value is, stands for?
The 126
Yeah, what is it?
molecular weight of
Yes,
iodine.
molecular weight of iodine. Thank you. So, and its units, what's the unit of molecular weight? Do you remember?
Grams per mole.
Grams per mole. Thank you. So we 126.9 grams per mole is just for you to remember is the molecular weight of your iodine. Okay, so
Diatomic iodine.
huh? Yeah, there's one more of that. Oh, the equivalence of this equals the equivalence of that. Yeah. Right? What's the molecular weight of iodine? Now you confuse me. Can we Google it?
Yeah, that should be good.
I just want, because here you have one more, here you have two. I wonder if it is.
Well, yeah, because.
Yeah,
and
you have
that's-
1 and 2, huh?
It's 2 there, yeah, because then the way that works is when you.
Yeah,
the
exactly.
two
So this
sodium.
is 1 iodine 1, right?
2,
2.
because you start with 2 iodine and then you end up with 2 Na iodine,
All right.
so it's the same.
Okay, got you. He got it. Okay. All right. The next one is another characteristic of any oil. It's the saponification value. So we use it to determine the average molecular weight of triglycerides or fatty acids in your sample. So it's a characteristic of the average molecular weight of the most dominant fatty acid in your sample, in your oil. So that is when I ask what's the saponification value, you define it as it's an index for average molecular weight of triglyceride and specific fatty acid in your sample. And it is, the unit is milligram of KOH required to saponify 1 gram of sample. So it's a saponification reaction. So in saponification, as you know, and you might remember from fatty acid chain analysis, you have a base that reacts with your triglyceride, breaks off the glycerol, release the fatty acids. So in this case, you have KOH. So it's the milligram of KOH required to saponify 1 gram of fat. So what we do again here is we saponify with excess KOH. So you put your oil, you add to it specific amount of KOH, you reflux, and then you let it reflux for about 30 minutes, 60 minutes, I don't remember, somewhere in there. And then you will get the glycerol and fatty acid salts. So again, you run a blank. The blank will not have your oil. So all of your KOH is there. And therefore, the blank will be needing higher amount of HCl to reach to endpoint. So again, in your equation, volume for blank minus volume required to titrate your sample. So basically here, your KOH is titrated with HCl in presence of an indicator. So you titrate to, again, I think a clear endpoint. Those we did last day.
Yeah.
Yeah, so it was, yeah, so it's pink with the base and then you titrate to clear. Okay, so basically here, the equation, if you see here, it's milligram per gram. So there is no 100 because it's per 1 gram. So you only divide by the weight of the sample. And another thing is missing. What is missing? 1,000 in the bottom. Why? Because it's milligrams. So if you remember, so this is in milliliter. We usually divide by 1,000 to convert to liter because normality and molarity are per liter. So you always correct the milliliters to liters and then you divide by 1,000. But here, what is this number for? What is that? So it is molecular weight of KOH. Okay, so grams per mole. So it's grams per mole. And then you have here, it's the 56.1. This is molecular weight of KOH. So your final value will be in gram unless we multiply by 1,000 to give me in milligrams. So if I multiply by 1,000 and divide by 1,000, they cancel each other. Are you following me? Right? Because it's in milligram, I would need to multiply by 1,000. But since here it's milliliter, if I divide by 1,000, these two will cancel. That's why I don't have them. All right? Milligrams per gram. I don't multiply by 100. I don't divide by 1,000. Anybody would like me to repeat? Oh, all right. So now the fun stuff. Let's take a piece of paper. Calculation. A lot about calculations the second half of the class. Okay. So it's a puzzle. Here we're going to use saponification value to get the average molecular weight of the fatty acid in this olive oil. The main fatty acid in olive oil is what? What fatty acid is the main fatty acid in olive oil? Oleic acid, C18-1, 1 double. Okay. So in this exercise, we're going to calculate the average molecular weight of C18. I'm going to give you a few givens here to help you think this through. Well, first of all, molecular weight of KOH is 56.1. Molecular weight of glycerol, you need that, is 92. So grams per mole is your unit. And then molecular weight of water, you need that too, is 18 grams per mole. All right. This is the equation you want to remember. In the final, if I tell you write the chemical equation, I don't want you to draw the triglyceride. I would just say triglycerides plus 3 KOH gives you a glycerol plus 3 fatty acids. So you need that equation. Another thing you want to remember is that three fatty acids plus glycerol will give you, what will it give you?
One triglyceride.
One triglycerides, and it's a condensation reaction. 3H2. So this is important for molecular weight calculation. 3 molecular weights of fatty acid plus the molecular weight of glycerol equal the molecular weight of triglyceride plus 3 molecular weights of water. I need to know the molecular weight of triglyceride because I know this. I know this. Then if I know this, then I can get the free fatty acid. So I need the molecular weight of triglyceride. So what is the given? The given is the saponification value is 190 milligram KOH per gram of fat. So 190 milligram of KOH per 1 gram of fat. First thing, the units are not the same. So what do I need to do? Convert this into grams. So 190 milligram equals how many grams? Huh? You divide by 1,000. 0.19 grams. So 0.91 gram for 1 gram of fat. Then I go and think about this equilibrium of an equation. Now I'll give you 2 minutes to think about it. I gave you everything you need to know. There's one last thing you have to think on your own. So I'll give you a moment. Anybody with any hints? How to go about this? Not looking for a final answer. Any hint of how to go about this?
Stoichiometry.
Huh?
Like you balance the equation.
Yeah. Yes, value the equations to stoichiometric. Okay. So I have here 1 mole, right? Reacting with 3 moles. And another given, I have 1 gram is going to be saponified by 0.190 grams. Okay, so I have this to that, and 1 mole of triglyceride is how many grams per mole? This is what I'm looking for. So how many grams I have per 1 mole of triglycerides? That's what I want to know, because that would be the molecular weight that I want here. And I already know I have 3 moles of this, and I know the molecular weight of KOH. So that would be 3 times 56.1 grams per mole. Because it's 56.1 gram in 1 mole, and I have 3 moles, so I multiply. So basically, I'm solving for X, right? Solving for X. So that would be 3 times 56.1 grams per mole times 1 over, that's 1 gram, okay, over 0.190 grams. So grams will cancel. My answer will be unit of grams per mole. What would be the answer? Anybody questioning how we got there? It's all clear? There's going to be a question in the final. Okay, good.
295.
3 times 56.1 divided by 0.19. 8. 8. Great, grams per mole. So now I have the molecular weight of triglycerides. I can solve for fatty acid. So basically, 3 fatty acids will be equal 885.8 grams per mole plus 3 times 18 grams per mole minus, I'm bringing this over here, 92 grams per mole of glycerol. What does this give me? $849. Did you all get that?
Oh, sorry, I'm doing that 3.
What? No, not correct? Can anybody, can you do the math, please? By calculator, so 885.8 plus, is this 54? Plus 54 minus 92.
I got that.
Huh?
847.8.
Okay. Now, this is the molecular weight of 3 fatty acids. What would be the molecular weight of 1 fatty acid?
$82.6.
2
82.6.
grams per mole. Yes, and this is, my children, the molecular weight of oleic acid. the average molecular weight of oleic acid. So here's the equation without putting any units, but it's basically all of this. So you need all of this detail when you answer in the exam. You need to know the units because it helps you canceling units, helps you know what you're looking for. So here's just a brief abbreviation of everything. If you feel more comfortable, you can take a picture of the wall of the board. Or if you wrote it down, take a picture on your piece of paper and then give the piece of paper later to Jean. Any question about this? Without me in it. Okay, good. So moving on. Oh, I'm a little ahead. Okay. So next thing that you did or will do on Wednesday in the lab is measuring free fatty acids. So what does that tell us is the amount of free fatty acid liberated upon hydrolysis of triglycerides, whether it's hydrolysis by endogenous enzyme lipase or hydrolysis due to processing in the presence of heat and water. It tells us it can be an indication of adequacy of refining. So on Thursday, you're going to get, or on Wednesday, you're going to get data of refined olive oil and virgin olive oil. You're going to see a difference in the fatty acid content. Hydrolytic acidity, age of frying oil. So the longer it's used for frying multiple times, the more you're going to have free fatty acid. And it's basically, since you are measuring an acid, we're going to talk about titrational acidity on Wednesday. So basically, you are titrating with base. So at equilibrium, percent or equivalence of base equal equivalence of acid. So basically the same thing, same principle of derivation. In this case, you run a blank. The blank doesn't have any fatty acid in it. So the blank will be close to 0. So in this case, it's a sample minus blank. Again, normality of the NOH you're going to use. And again, you're going to use phenolphthalein as an indicator. And here, we use the molecular weight of oleic acid. In this case, we always calculate assuming oleic acid molecular weight, and same everything, divide by the weight of the sample, divide by 1,000, correct milliliter to liter, multiply by 100 because it is a percentage. We can convert to any other fatty acid or main fatty acid in the oil by multiplying by a conversion factor. We get that from a table. But anyway, usually you calculate using oleic acid. All right, so measuring the present status of oxidation. So it's the most common, there are a couple common ways. First, you measure primary oxidation products. And primary oxidation products are peroxides. And then you can measure secondary oxidation product. There are multiple secondary oxidation products that you can measure. Hexanal, for example, is a secondary oxidation product. Malonyl aldehyde is a secondary oxidation product. You can specifically measure malonaldehyde, or you can measure aldehydes in total aldehydes. But in the lab, you're going to measure peroxide value. So again, when I tell you define peroxide value, it measures peroxides, which are the primary products of oxidation. So the first products of oxidation, basically. And the unit in this case is milli-equivalent, not milligrams, not grams, it's milli-equivalent of peroxides per a kilogram. That's different now. milliequivalent per kilogram of sample. Who decided this and why? I have no idea. But it is so, it is milliequivalent per 1 kilogram of sample. So a freshly refined oil or fat, very fresh, will have 0 peroxide value. Some of you did lab today, your oils did not necessarily have 0 peroxide, although you opened the bottle today in lab. That is because they brought it from the shelf, and on the shelf, oxidation stops. So it's very rare that you buy oil from the shelf and it is very fresh still. So you will get a peroxide value no matter what when you get it off the shelf. All right, so here what happens that if you have peroxides, you add potassium iodide as a reagent. The potassium iodide is going to react with your peroxide, and then you will get iodine. Again, here with the iodine, you will add starch, you'll get the blue color, and then you titrate with sodium thiosulfate to color this. In this case, your blank should not have a peroxide. So your blank will be close to 0. So in the equation, it is sample volume minus blank. Okay. All right, so it is milliequivalent. So that means volume times normality at equilibrium equal volume times normality. So volume times normality of iodine equal volume times normality of sodium thiosulfate. And because it's milliequivalent, I do not correct, it's not equivalent, it's milliequivalent, so I do not correct milliliter to liter, so there is no times 1,000. And since it's per kilogram sample, not 100 grams, so 1,000 grams of sample, I multiply by 1,000. All right, so if you remember the unit, you will remember the equation. All have similar derivation. It's just based on the unit, you will remember the equation. There is no molecular weight here because it's milliequivalent. It's not unit of mass. So you do not use molecular weight. It's equivalence unit. So no molecular weight of anything, iodine or anything. Okay, so that gives you. Oh, there's a question there. So a very freshly refined oil will have a value of 0. What about a very, very rare?
Why does still have a low peroxide value since we'd be in like the later stages of oxidation?
Exactly. So what you did in the lab on Monday, which you will do on Wednesday, is you will look at the peroxide value over time with accelerated storage. In the oven, heated oil at different time points. So what happens is you will start. Okay. So you will start. Here's your peroxide value. Let's assume you will never get at 0. Let's assume you started here. You will see, traditionally, you will see over time, here's that. You will see an increase in peroxide value. And then you will have secondary metabolite formation. Then your peroxide value will start decreasing and potentially it can get to 0. So here you might still be generating. So here the rate of generating peroxide is larger than the rate of generating secondary metabolites. Here the rate of generating secondary metabolites is larger than the rate of generating peroxide until no more peroxide. All peroxide moved on. So a very rancid oil will have a peroxide value of 0. How do we know it's rancid? Just smell it. It's gonna be awful. Yeah, so that's what it is. A very fresh oil and a very rancid oil will have a peroxide value of 0. Oh, in the lab, you're gonna see some anomalies. You're going to see oils that don't behave like we expect. You're gonna see oils that start really here high, and then you're going to see a decrease. That means we basically towards the end of the shelf life. So you start with really high peroxide and then start decreasing over time. You're going to see oils that behave like that. So you start here and you never see a plateau. Because the oil is still oxidizing, you're still getting high peroxides. Maybe it's very polyunsaturated, so the rate of peroxide generation continues to be higher than the rate of secondary metabolite. So you're going to see all sorts of oils in the lab. Not all of them are going to form this nice expected curve. Maybe one of them might. Okay, so in the last couple of minutes, continue with the current state of measuring oxidation. So another one is NCD value. So this is a measure for all total aldehydes that could be generated. So aldehydes are secondary metabolites. So they will react with the reagent NCD to give you a chromogen. That means colored substance that you measure absorption. Totox value takes into consideration secondary metabolites and peroxide value. So you get the NCD value plus 2 times peroxide value. So that is kind of combination of primary and secondary oxidation. And these are just examples of numbers here. 2 other methods really quick. I'll keep you 30 seconds more. Hexanal is a secondary metabolite. It's a volatile, so we can measure it using GC, FID. Very easy. The sample, you don't even have to extract the oil if it's not an oil. If you're measuring in a, let's say, flour sample, you can put it in a flask. And the head space, that means you take a volume of the air above the sample, which can contain hexanal, and that gets injected into the GC. It correlates well with sensory evaluation. It's very easy. We use it a lot in the lab to determine oxidation of flour samples. The last one I'm going to talk about is T-bars, which is thiobarbituric acid reactive substances. Very long name. T-bars is the common short name. Here we're measuring a specific secondary metabolite, which is an aldehyde, malonyl aldehyde, which is malonyl aldehyde is a derivative specifically of linolenic acid. So if you have oil that is very low in linolenic acid, it's not going to be very sensitive. However, it is used in meat because in meat you have high levels of linolenic acid, or considerably enough level of linolenic acid. So basically, malonyl aldehyde reacts with TBA, thiobarbituric acid, again to give you a chromogen, measure absorption, and it correlates well with sensory evaluation. Because it is not very sensitive assay, if you have low concentration of linolenic acid and you still want to use, you want to determine malonyl aldehyde, often use HPLC. Okay, I'm going to end here and then we'll finish a couple of slides on Wednesday after the quiz. But the quiz is up to here. So I already made the quiz, so there are questions. You don't have to study the protein characterization. So because of just moving schedules, protein characterization will be on the final. All right, so include studying fat characterization, everything up to this slide. Any questions? All right, study well.